Good afternoon, everyone. We are continuing with yesterday's lecture on power and torque in induction motors. So we will proceed immediately. Right. So where we left off yesterday, we had gone through the way in which we can calculate power and torque within the three-phase induction motors, and we said that it is a series of kind of drops of power all along from the input to the output, which was being shown. I think we showed it here. Yes, so you have starting from the electrical at the input side, you go all the way dropping various losses and converting them until finally you have mechanical power as the output of the motor. So today we are going to look at the example that we talked about yesterday. I'll just take us through it so that we can realize the process by which we analyze three-phase induction motors. So we'll go straight in with that. So now what you can see, the example that is given there, you have a few parameters of the induction motor. So the formulation of your example of your problem is given like that. You have various parameters for your motor. You have, you're given the voltage. You're told that it's a three-phase motor. You're given the voltage, a rated frequency, the number of poles, and the type of connection of the induction motor. And of course, you're given various parameters of the motor, resistances and impedances and reactances. Then they say that there's a slip of 2.2%, which is roughly what we talked about. Remember, we said the slip determines various other elements, which we will see going forward. And you're given rotational losses. That is the mechanical losses that the motor encounters before you can give kind of a useful power. So that has to be deducted from the output power that you would get. And for this particular problem, we have been told that rotational losses include core losses, right? That is a key one in how we approach the problem, because it indicates that certain elements of the equivalent circuit will not be as we have seen before. Then the problem asks, we need to find the motor current, input power, output power, and finally output torque. So all the ingredients that we need, all the equations that we need are based on what we had talked about yesterday. So we'll just go straight ahead. So the first step is to kind of visualize how our three-phase induction motor will look. So we do that by drawing the equivalent circuit. Okay, that's how our circuit looks like. So we have R1, X1, JX1. This was JXM, RC, JX2 prime, and R2 prime, right? This is the, R2 prime over S. So this is the familiar circuit that we had drawn, not the modified one that I showed you yesterday, but we will be using the main equivalent circuit that we had derived last time or the previous time, okay? And so straight away, some of the elements we already know. So we have 0.75 ohms, 5 ohms for the R1. JX1 is given by 1.2 ohms. JX2 prime is 0.5 ohms. These are all complex. R2 over S is 0.2 ohms over the speed, which will be given as 2.2%. We'll calculate that shortly. XM is given as 25 ohms. Now, one thing, what I've already mentioned, the rotational losses are included in core losses. That means RC, in this case, has already been factored into the 1100 ohms. So in this case, that means our circuit diagram here, we will not include RC. So it is as if it is an open circuit. The impact of RC will not be used in the calculation since we have referred it to the losses. So we will go ahead and erase that from our equivalent circuit. And therefore, we are left with that as our equivalent circuit. So we can start off by doing a bit of analysis. Let's start with motor speed. So let's look at how we would do motor speed. Okay. So the motor speed, what we are looking for is essentially N. Okay, and for completeness, we will do N, and we will also use the angular speed. We'll calculate both of them. Now, N, as we know, is related to the synchronous speed through slip. So slip is equal to Ns minus N over Ns times 100 in the case of a percentage, all right? And we know two of those, so we want to make N the subject. So we say N is equal to, or we can be able to calculate both. So we say N is equal to what? Let's start by rearranging a bit. So if we bring to the other side, say 100S times 100S, it is S times NS over 100 is equal to Ns minus N. And if we rearrange once again, you will have N is equal to Ns minus S Ns over 100, which then becomes Ns into 1 minus S over 100, right? So that's a form that we can use to calculate the motor speed, okay, the mechanical motor speed. So second step is we look for synchronous speed, and we said synchronous speed is equal to 120 F over P, simple as that, which is equal to 120 times frequency was 50 Hertz. So 50 Hertz over the number of poles. So we take the raw number of poles, not the pole pairs, but the number of poles, which are 4. And that gives us 120 times 50 divided by 4. That should be 1,500, which is your standard RPM. Okay, so this is synchronous speed. This is a key component. This is fixed and does not change as long as the frequency of the supply does not change, which means that unless you're running your machine in America where they have 60 Hertz, you will always have the same speed. So let's get our motor speed, mechanical motor speed. That will be N equals to 1500 into 1 minus S over 100. S was here, 2.2%. We've already seen it. And so we can calculate that. So 1500, it's already on the calculator, times bracket 1 minus 2.2 divided by 100. And that gives us a similar figure. It is slightly less, which is what we expected, 1467 RPM. Okay, so that is your expected mechanical motor speed at that particular slip. And I'll remind you, as I'll keep reminding you, for those of you who will, go forward into industry, especially heavy industries where three-phase induction motors are the most used machine, note that your speed of rotation, so the mechanical speed and the synchronous speed, are always closely related to each other because your slip is very small. There is no day you'll have a slip of 60% in a motor that is running operationally. or rotating in its normal application, as I can put it, right? And, at this point, I'll remind you all of the assignment that you have. I've answered a couple of queries on that. Please do, try to look out there. You still have about 2 weeks left. Try to go out, try to explore, try to see some of the applications that these motors are used in, and dig a bit deeper into how they operate, and try to see them even in operation. Don't just observe them when they're stationary. Ask the people who operate them or the people who use them, what is this being used for? What are the challenges that they encounter? If the thing ever breaks down, what causes it to break down? Does it overheat? Things like that, whether it's a posho mill or a treadmill or conveyor belt or a pump or whatever it is. Generally, these characteristics and these elements will hold true for all of them, right? So, as I said, those who will be going into industry, always remember the speed of an induction motor is only comparable to the frequency of that machine. So that's your motor speed. Let's look at kind of angular speed. So omega m. Now omega m is given by n times 2 pi over 60. So it's just a conversion of the speed. So you'll have 1467 times 2 times pi divided by 60. That shouldn't be wrong. Yes, there it is. Okay, 153.6, let's call it 62 radians per second. Okay. So input current, we will look at it from the point of view of the supply. So we have number 2 is input current. Okay, so how do we get input current? So now input current, when we look at our supply here, so our supply input current is I1, which is there. Now we will also have IX, is it IX or IM? IM, sorry. And you have I2, okay? So we are looking for input current, and we do know our voltage, our phase voltage. And also we have a complete equivalent circuit. So we have all the various impedances across the board, okay? So we will now use these ones to find the current using simple Ohm's law, right? We have a total impedance, we have a voltage, and we have a current. So we have a complete circuit that we can analyze. So the first thing we need to do, we had said we would need to calculate R2 over S. So that's the first one that we take. R2 prime over S is equal to 0.2 over 0.022, because that's a percentage, which is given by, so it is 9.091, let's say, ohms, right? So first of all, as we are looking at our circuit, let's take, we start from the farthest. So from our circuit analysis, we know we start from the farthest point coming backwards. So the farthest point would be the combination of these two. So let's call that, say, Z2, because it is in the arm of Z2. So we say Z2 is equal to R2 prime over S plus JX 2 prime. Back the calculator. So we already had that. So JX2 prime, we have said, is 0.5. So 0.5. Right, so we have that. So Z2, which is indicated there, 9.091 plus J 0.5 ohms. Next, so we are coming closer to the beginning. So you now have ZF, Z2, and you have your XM here. Let's create something called ZF, which is a combination of the two. And your ZF will be represented by ZF is equal to Z2, which is this arm, and XM, which are parallel to each other. So that will now look like, talk of them being parallel. So this is product over sum. So it is Z2 JXM over Z2 plus JXM. So that gives us 9.091 plus J0.5 times J25 over 9.091 plus J0.5 plus J25. So we take all of that Okay, so that gives us, after working that out, you have 7.75, let's call it 3, plus J 3.254. Okay, so that is our ZF, which is up to the point that we have indicated here. That is our ZF. So finally, the total impedance of the entire circuit will be equal to ZT. We can allocate ZT, which will be R1 plus JX1 plus this ZF that we have just calculated, all right? Because they are all in series to each other. So you've created an equivalent ZF over there, okay? This is just circuit analysis. So now we add them all up together. So ZF is already on screen. That will be, R1 is 0.75. $1.2 plus 7.753 plus J 3.254. So we add those to the rest, and we should be able to get the answer, which is the total is equal to 8.5, let's say 03 plus J 4.454. These are ohms. This is your total impedance of the entire motor. So as seen from the supply, what the voltage, the phase voltage sees, that is your total impedance given as one element. And this is the importance of having, you know, all the derivations we went through when we were doing the equivalent circuit, so that you can have it all on one simplified circuit with all the elements being represented. So straight away we can be able to say current I1 is equal to V phase over Z total. Okay, and we know our V phase, we've been given our line voltage, which is 415. You will divide it by √3, so 415 over √3 times ZT, which will be equal to 415 divided by √3 times the answer, hoping that will come out correctly. Yes, that is the correct answer. So 22.11 minus J 11.583 amps, right? Now we also want to get the various elements of the current. So we would want to put it also in polar form so that we can know the phase angle of the same. So we'll convert the same answer into polar form, and that will be, it is an equivalent form, 24.962 at an angle of negative 27.648 degrees, and these are amperes. Okay, so there we have your input current that is being fed into the machine. So you know that already. Input power, let's talk of input power. So input power will be given by, you already know the voltage and the current at the source. So it can be given by root 3 times V, which was our line voltage. Let's just label it VL, times I1 times cos theta, which is our angle that we received here. However, we can also say that this element here is given by the real part of the current. Yeah, remember we are looking at power. So the real part of the current is the active power, and the reactive part of the imaginary part of the current is the reactive power. So a shortcut for this would be you multiply that by the real part, which we have already known in the previous one, right? So that is also acceptable. So if we were to say 415 times 22.11, that would still be an acceptable answer. Or you can do the long way, which is 24.962 into the cosine of that. But for now, I will just do that one for 15 times 22.11. So that is giving us 15,892.7 watts, okay, which is equal to 15.893 kilowatt, right? So that once again is our input power, okay? So far, I think we are so far so good. Now we start looking into deeper aspects, you know, taking real advantage of the analysis that we are talking about. So let's look at the the output power. So now here we have an interesting situation where we can only see the current and the power and the voltage and the frequency that is being supplied. Yet we want to know what is the output power that is mechanically made available to the motor. So let's see how we can figure that out. So here we will take advantage of our sequence of events, right? So now if we remember, we just as a reminder, you know, this is our diagram as it looks. So we had the sequence of events. You had your input power, stator copper losses, core losses, air gap power. Then air gap power drops the rotor copper losses, and so on and so forth. So that is the sequence of events that we need to go through in order to find our output power. So we go step by step. So our output power, working backwards, is equal to converted power minus rotational losses. Okay, rotational losses we were given up here as 1,100 watts, okay, or 1.1 kilowatts. However, the other element, converted power, has not been indicated. So let's see what is converted power. Okay, converted power, we had a previous equation where we had said it is 1 minus S of the air gap power. Remember, we showed that yesterday. I believe we have it somewhere here. That was air gap power. So we said here it is, all right? So this is, we are making use of that equation, okay? Converted power and the relationship it has with air gap power, right? So far, we've gotten back to the air gap. We are in between the rotor and the stator. So we are somewhere around here at that point. That is air gap power. So moving further backwards, how is air gap power related to input power? So we say P AG is equal to input power minus stator copper losses minus core losses. But remember, core losses have already been factored into your rotational losses, so they will be factored in at this stage, okay? So now where we have reached, we can now be able to say input power minus stator copper losses. So we need to know, we know input power, we need to know what are our stator copper losses. So stator copper losses, as we had said yesterday, it is simply the value of the resistance or the value of heat lost in the resistance that is the R1. Okay, so therefore we can classify it, or we can say that it is 3 times I1 squared, which we know, times R1. So we know all of those, and this is given by 3 times I1 squared is there. We take the full quantity of I1 squared, not the real part only. 24.962 squared times R1.75. Okay, so let's calculate that. Right, so that is 1,401.98 watts. Right, so working backwards, so we now go to air gap power. So air gap power is equal to input power, which we got as 15,893. 15,893 minus 1,401.98. So it is 15,893 minus the answer we have just gotten. So that gives us 14,491 watts. Then moving further backwards, so converted power is equal to 1 minus S, that was 0.022, into 14,491. So that answer again times 1 minus 0.022. So that gives us 14,172 watts. And finally, now we have reached the stage where we have calculated everything. So the output power is equal to converted power minus rotational losses. So that's 14,172 minus the rotational were 1,100. So 1,100 watts. And this finally gives us 13,072 watts, right? And that is our answer up to that stage. Okay, so that's your output power, right? And finally, let's look at output torque. So the output torque is related to the output power. We are saying output torque is related to output power. We look at it as follows. So load torque, which is the same as output torque, is equal to P out over the mechanical speed, and that gives us 13,072 over mechanical speed we had calculated up here. It was 153.62. So 153.62. 13,072 is still on our screen. 153.62. So the load torque is equal to 85.095 Newton meters. So that is the torque that is available at the shaft of the machine, right? And I think one additional element we can add to this, we can call efficiency, which is a good way of relating the output and the input. So in this case, our output was 13,072, which is here, and our input was 15,893. So 15,893, 13,072 divided by 15,893. That gives us about 82%, 82.25% efficiency. Okay. And so that is a bit of analysis that we can do on induction motors. I mean, you can see induction motors seem to be not very efficient. It's not the most efficient motor that is available out there. Technology has moved on or improved over the years, as we will see in the next unit, in the next semester. There are certain motors that do have better efficiencies than this, but for a motor that has, very simple construction, you remember, just to go back, there were that photo. Yeah, you can see, as we said, there are no, there are very few moving parts that are there within your three-phase induction motor. And for that, to get an 82% efficiency, that's fairly good. That's a very good return on investment. So this is part of the reason why we say the three-phase induction motor is actually a very good engineering solution that provides a robust, reliable, and, as you have seen, relatively efficient way of converting electrical power into mechanical power. And so on that note, I think we can end it there.